So hi guys, welcome back to the channel. Today we are tackling a system design classic that is deceptively simple but incredibly deep, building a global URL shortener like Bitly. Now, if you're thinking that isn't this just a hash map that points a shorter string to a longer URL? Think again. Imagine you're not just shortening a link for a friend. Imagine you are the backbone of the internet's redirection layer. We are talking about billions of new records every month and a read to write ratio that is absolutely massive. Here is the real challenge. How do you generate a unique 7 character alias for a URL in a distributed system where multiple servers are writing to the database at the exact same time? How do you prevent ID collisions without creating a performance bottleneck? And most importantly, how do you handle a thundering herd where a single viral link from a global influencer hits your system with millions of redirects per minute? So if your system lags for even 200 milliseconds, you have broken the user experience. In this video, I'm going to stop treating this like a textbook exercise and start treating it like a production grade engineering problem. We are going to walk through my 7 step delivery framework where I have functional requirements, non-functional requirements. Together, I call it requirement gathering. The third one is listing core entities. We also have API as well as interface design. We design the data flow. We also have the HLD and deep dives. So this is just a mental model which I follow during interviews. By the end of this, you won't just know how to build a URL shortener, you'll understand the core principles of distributed systems and scalability the top tier companies look for in a senior engineering loops. Now that we have framed the challenge, let's get into the requirement gathering phase. In any tier 1 system design interview, if you don't define your boundaries here, your design will collapse later. We'll break this into functional and non-functional requirements. So firstly, we move on towards the functional requirements. So what is the core contract of our service? That is URL shortening. Our system must ingest a long URL and return a unique shortened alias, which is as simple as that. The second thing which we should be dealing with is the accessing. That is the most critical part. When a user hits that short link, our system should resolve it and perform a 301 or 302 redirect to the original destination with a sub-millisecond precision, which is very important in our case. Now we move on to the non-functional requirements. This is where our engineering gets interesting. This is where we talk about the system's DNA. So the first one is the uniqueness and collision resistance. We cannot have two different long URLs mapping to the same short code. Our generation algorithm must be mathematically sound and collision resistant at scale. The second thing which we will be checking on is cap theorem. If you would have seen my previous video, the second non-functional requirement is generally based on the cap theorem, where partition tolerance is non-negotiable. And here, in the world of URL shortness, availability is king. If your system is down, the links are dead, and the internet breaks for our users. We are willing to trade off eventual consistency for high availability. If a user creates a link and it takes a few milliseconds to propagate globally, that's fine, but the redirection service must never go down. The third one is ultra low latency. Redirection is a blocking experience for the user. We need to ensure that our lookups are lightning fast, which means heavy reliance on distributed caching strategies. The fourth one, what we are talking about is the scale, where we are designing for a massive throughput. Our target is to handle 100 million new URLs generated per day and support over 100 million daily active users. So these are very huge numbers when we are talking about them. Is the 100 million URLs generating per day and via 100 million daily active users. When you're dealing with such big numbers and such big writes to the DB, obviously, because when we have 100 million daily active users, you will have a lot of writes to your DB. So we are not just managing data, we are managing a fire hose. Now that we have laid out the requirements, but as engineers, we don't just build based on feelings, we build based on math. To design the right storage and throughput strategy, we need to do some back of the envelope calculations. These are the calculations I generally like to do after declaring my non-functional requirements. So let's quantify the fire hose we talked about. So the first one is where we said that we will be having 100 million URLs getting generated per day, and we need to calculate a write throughput for this. So taking 100 million and dividing it by seconds in a day, we get around 1160 writes per second. And if we assume that we would be having a 10 is to 1 read to write ratio, our read throughput jumps to 11.6k requests per second. So this is a huge number. This tells me immediately that our redirection layer needs to be heavily optimized for reads, likely using a robust caching layer to avoid hitting the database for every single click. Now the second thing is about storage estimations. Now that we have a long-term horizon where we are building this for a, let's say, 10-year retention period, how much data are we actually talking about? So as I said that we will be having 100 million daily active users, and sorry, we'll be having 100 million URLs also getting generated per day, and let's say we have multiplied it by 365 days, that number of days in a year, and let's say for 10 years if we calculate it, we will be having around 365 billion records in our database. And if we assume a lean data model as well, averaging about, let's say, 100 bytes per record, which stores, let's say, the short code, the long URL, and the metadata mapping, we are looking at 36.5 terabytes of storage. This is a huge storage. A single relational database instance is not going to cut it. This calculation is a massive red flag that tells us that we need a distributed database and a sharding strategy from day one itself. So, with our calculations handled, let's define the core entities now that make up the heart of this system. From what I have written over here, you can see we really have three primary components that need to interact. The first one is the original URL. Now, this is the long, complex link provided by the user that needs to be shortened. This is basically our source, the destination where we eventually want to send the traffic to. Then the second thing is the short URL. This is the manageable link that the user receives back from our system. This is the alias that can be easily shared across social media or messages, and it's what our system will use to look up the original connection destination for. The third one is the user. This is the entity where we are talking about the person or the account who wants to shorten the URL. It's important to track this so that we know who owns which link and who is interacting with our service. Now, finally, if we try to connect these entities and try to build a flow out of it, here is how it would be. A user will submit an original URL to our application, and in return, the system generates and maps a short URL to that user. When someone clicks that short link, our system identifies the connection and redirects them back to the original destination. So, this is how I look at the core entities. All right. That now that we have our core entities, we need a way for the world to talk to our system. This brings us to the API design, or what we call at system interface. To keep this lean and efficient at scale, we are going to focus on two primary endpoints that drive the entire user experience. So firstly, we need a way to generate these links. So we exposed a post request, which is, let's say, slash URLs, where the client sends a JSON body containing the long URL, the massive link we talked about earlier. In response, our system processes the request and returns a JSON object containing the short URL. This is where the magic happens behind the scenes, taking that long input and returning a clean bitless style link with a unique shortcode at the end. Now, the second thing is the redirection endpoint. This is the most high traffic part of our system. This get request. When a user clicks on a link like, let's say, bit.ly slash xyz123, they are hitting our system with that short code, which is over here. And our job is to perform a lightning fast lookup for this. So instead of just sending back the long URL as text, we issue an HTTP 302 redirect. This tells the user's browser that, hey, don't just stay here, go directly to the original URL. We use a 302 redirect here, which is a found status to ensure we can still track analytics on every click before the user lands on their final destination. Yeah, so let's move on to the high level design now, which is the next step according to our delivery framework. So here we look at the actual architecture. Here we are going to focus on the right path, how we fulfill our first functional requirement, that is a user submitting a long URL and receiving a short one, which is as simple as that. Now, the process starts with a client which hits our system with this particular post URL, which we just designed in our API interface. This request lands us on our primary server, which acts as a brain of the operation. Now, here in this primary server, we don't just blindly shorten everything that comes our way. As soon as the request hits the primary server, we perform two critical validations. The first one is this actually a valid URL? Like we check the syntax and the protocol to ensure that our system stays very clean. The second validation we do is about the deduplication. This is an important optimization. We check our records to see if the exact long URL has been shortened before. If it has, there is no need to create a new record. We simply return the existing shortcode. This saves us massive amount of storage over time. So basically these two validations are the ones which are taken care when any post call comes to us. So if the URL is valid and it has passed our all validations which we just discussed, we move on to the generation phase. Here what we do is we take the long URL and pass it through a hash function, which is written over here. If you see this f of x is the hash function. This function transforms the long string into a compact unique shortcode. Like let's say you can see here, which is ghc123i, which is a shortcode generated by my hash function. So once we have that code, the flow is very straightforward. We save the record to our database. So our schema here is very lean, let's say, because what we are storing into the database is just the short code, the original URL. This is basically the mapping between the short URL code and the original URL, and this is metadata, which is creation time and let's say created by, which will basically have the information about the user who wanted to create this thing. So once the DB write is confirmed, we return the final short URL to the user, which is this particular URL over here. So this completes the first half of our system's promise, that like by centralizing this logic into our primary server and ensuring we validate before we hash, we keep the system consistent and efficient. But this is just the right side. The real challenge comes when we have to handle those billions of reads requests, which we will dive into the next functional requirement or the next part of this HLD. Yeah, so now let's look at the second functional requirement, which is accessing the original URL using the shortened link. This is the high traffic read path which we just discussed. Now, when a client performs a GET request with a short code, it reaches to our primary server. Now, the server's first job is a lookup. It searches the DB for the original URL corresponding to that specific code which the client has provided. Once we retrieve that destination, we have a major architectural decision to make regarding HTTP redirects. So there are two primary ways to handle this, and each has massive implications for our system. So let's talk about them one by one. So the first one is a 301 redirect. Now, this 301 redirect indicates that the resource has been permanently moved. So what is the implication of this particular 301 redirect is that browser will cache this response. Now, this means the next time a user clicks that same short link, the browser won't even talk to our server. It will go straight to the long URL. Now this reduces the load on our servers, which is great for scaling, but again we lose all visibility if the request bypasses us, and we can't have all the analytics which we might want our application to have. So this is about 301 redirect. Now let's talk about 302 redirect. This redirect indicates that the resource is only temporarily located at a different location, and this basically makes browser to not cache the response what we have written from our service. So every single click on that short link is forced to go through our server first. So this is like we are forcing the request to come to our server once, get the short URL, get the long URL for that particular short code, and get a redirect from there. So in our case, we usually have some parameters on which we decide what to choose between both of them, a 301 redirect or a 302 redirect. So here we have the request passing through our service, and we have, if let's say we consider 302 as the thing which we would return, then we have some benefits out of it. The first one is like we will have more control because we will be maintaining the total authority over the redirection flow, I would say. Then if we talk about flexibility, because our browser isn't caching the link, and we can change or update the destination of a short URL in future if needed. So this provides us the flexibility. And the third thing is about analytics. This is the big one because every request hits our server, we can perform real-time analytics and track click counts, timestamps, and user demographics before sending them on their way. So this is just for analytics, and this will help us because the request. Okay, so now that we have our high level architecture sorted, we will try to move on to the deep dives according to our delivery framework. So we need to answer the most critical technical question over here is how do we ensure that these short URLs are actually unique, compact, and collision resistant at scale. So this is the one thing which we will look into this particular deep dive. So if you look at a short core or basically the short URL code, it will typically consist of characters ranging from 0 to 9, or small a to small z, or capital A to capital Z. When you add this 10 digits and 26 lower cases and 26 uppercase characters, you get 62 possible characters for every single slot in your short code. So now if we have a short code of, let's say, length n, the total unique combinations which we can generate is 62 power n, because we will be having n slots, and for every slot we will be having 62 possible characters which we can put in that slot. So if we if we have n slots, then it will be 62 power n, obviously. So earlier in our calculations and in the back, maybe I mean the back of the envelope calculations, we got to know that for if application sustains for 10 years, we will be having 365 billion records, which is nothing but we will be having 365 billion long URLs submitted by the users, and we would have converted them into a short URLs over 10 years. So how do we find the smallest n which handles this particular thing? So by solving this equation where 62 power n should be greater than 365 billion, we start plugging the values into n. So let's say if you put n equal to 5, we get 916 million, which is not even closer to 365 billion. Then we get n equal to 6, which is 56 billion, which is a bit close but not exactly our target, which is 365 billion. Now when we come to n equal to 7, the math shift gears. For 62 power 7, it gets us around 3.5 trillion possible unique strings. So by choosing n equal to 7, basically we aren't just hitting our target, we are creating a massive buffer, meaning we can handle nearly 10 times of our projected capacity without even running out of unique IDs. This is how you build for a decade of growth. Now, here we would explore two types of hash functions basically for our URL shortener. And the first one is hash plus collision resolution. So if you see over here, I have a URL and I have this particular three hash functions with me, which is crc32, md5, and sha1. When I gave this particular URL to this hash functions, I got the three respective hashes, which are this three strings which you can see over here. Now here is a practical catch. If you see, standard hash functions, which I just mentioned above, produce values much longer than 7 characters. So here only if you see the shorter one, which is crc32, had 8 characters in it, which is greater than 7. So if we look over here, that let's say if we try to build some approach on this particular thing, one common approach which would come up is simply collect the first 7 characters of the hash. But as any senior engineer knows, truncating a hash leads to collisions where two different long URLs might accidentally produce the same 7 character prefix, which is not acceptable to us, right? So that is why we need to have some collision approach where it is quite resistant to the collision. So we need to build some approach for this. So to resolve this, we use a recursive strategy as shown in my flow over here, where we submit a long URL to the hash functions, and once the hash function generates the hash for that particular URL, we extract the first, let's say the first 7 characters out of it, and we check if it exists into the DB or not. So the flow comes from input URL to the hash function, and then we get the 7 character long. We get some hash, and then we truncate we actually extract the first 7 characters. We check if it is present in the DB. If that thing is present in our DB, then what we do? So here, if it's a no, that means it doesn't exist into DB, then it's a happy scenario. We will actually save that particular mapping for that a long URL and the generated short URL for that particular URL given by the user. But let's say it is existing into the DB, what we would do? So we would recursively append some predefined characters to the original URL over here, and we rehash it. So when we rehash it, we will again get a new hash for that particular thing, and we keep this loop until we get a unique 7 character code which is generated, which does not exist into the DB. So this is a cyclic process or recursive process, where until and unless we don't get a unique 7 character long hash which doesn't exist into our DB, we'll be repeating this particular process. Now here here we again have one expensive operations. If you look closely here, we are constantly querying the database to check for the existence on every single write that we are making basically. So to optimize this, we can use Bloom filters. So if you see over here, every time when we come over here in the short URL part where we have generated the hash of it and we have extracted the first 7 characters, we check into the DB. So instead of checking into the DB, we introduce Bloom filters. So this is a space efficient probabilistic technique used to test if an element is a member of a set or not. In our case, the whole like the list of all the hashes which we have. So a Bloom filter can tell us immediately if a shortcode is definitely not in the database, and this allows us to skip the expensive DB query in the vast majority of the cases. So this drastically improves our system's throughput because Bloom filters are used in such cases only where it either tells us that it may be or may not be inside the database, or it is definitely not in the database. So these are the two things which Bloom filters actually tell us when we query something to it. So in our case, if it tells that the short code is definitely not inside the database, we would actually not go inside the database, and we would directly save it to the database rather than making a call to the particular database and increasing the maybe the read queries or what we are going to have in our DB. Now the recursive hashing method we just discussed, though it is working, it has some flaws. As we discussed, it is computationally expensive because of the potential for multiple DB lookups. So let's look at more elegant deterministic approach, which is base 62 conversion using unique IDs. So instead of hashing the URL directly in the above case which we were doing, here we assign every single record a unique numeric ID like a primary key in a database. We then convert this base 10 number into a base 62 representation. So you can think of this like converting between different numbering system, just like you do for decimal to binary. Here we would have decimal to a base 62 character set. So let's look at an example. You will have a better idea using it. Here let's say we have 11157, which is a base 10 number. It is into decimal system. So this is how we see 11157 as, and we are used to seeing this kind of decimal system because we follow it everywhere, which is 11157. This is the number, but how does it look like in base 62 format is what we will see. So the easiest method to convert anything to base 62 is we divide it by 62 at the start, and we recursively do this process. So what we do is, firstly we divide that number by 62. Here we get the 179 as the quotient and the remainder as 59, if you see over here. Again, what we 179, the thing which we got over here as quotient, again we divide it by 62 and we get a remainder as 55 over here. Again we recursively do that for because here we got the quotient as 2. Again we did again we divided it by 62, we got 0, and the remainder was 2 over here. So if you convert this 59, 55 and 2 into base 62, then we get it as capital X, capital T, and capital 2. So basically this 2tx is the base 62 representation of 11157. This was just an example. In our databases we will be having big long numbers because it is a numeric ID which we will be converting into base 62. Okay, so this technique is incredibly powerful because it is mathematically unique. As long as our ID generator provides us a unique ID number, the resulting base 62 string is guaranteed to be unique. So no collisions, no recursive checks in this particular example. So but there is a trade-off also. If you see over here, if we use a simple auto incrementing counters like some people use, let's say 1 2 3, then our short you code URLs become very predictable. And sometimes if something is very predictable, then essentially we might be compromising on the security of that application. So we should not be predictable. So here in this case, to make this production ready and secure, we won't use a simple counter. So we would use let's say a distributed ID generator like let's say Snowflake or a ticket server, to ensure that our IDs are unique across multiple servers while remaining non-predictable. So as you can see, I have written a sample record over here. So we would be having this as a unique ID which will be generated by any ID generator. Once we have this ID, we generate a short code for that, which is ZN9EDU, which you see over here, which is basically base 62 conversion of this particular ID. And once we have this ID generated, we have this as a record where we map this ID, short URL and long URL into our DB, whatever DB we are going to have. So it's built to scale to 365 billion records, which we calculated earlier now. And I feel this is the approach I think we should adopt going forward. So here we have solved the uniqueness problem now. But in a production grade URL shortener, speed is everything. If a redirect takes 2 seconds, the user experience is broken. Our goal is a sub-millisecond latency. So let's look at the 3 levels of optimizations which we can do to achieve this particular thing. So here, firstly, the most fundamental optimization which happens at the storage layer is, you can see, is adding an index. So we would actually add an index on the URLs table for the short code column. So think of this like the index at the back of a textbook. Instead of reading every page, the database can jump to the exact match almost instantly. So if we, this will certainly improve our performance, because then for every query we will not be requiring an order of n time but an order of login or order of one time, just to get if the short code is there or not. Okay, the second thing which we would see over here is some numbers. So firstly, if we assume that we are having 1 million users, and if daily they are calling the service, and let's say there are 5 redirects per user in a day, then we are looking at 5787 redirects per second. And if we consider 100x peak traffic, then it would be around 500k reads per second, again, which is a very big number. And while indexing is very powerful, but at this scale we cannot just rely on the database alone, we need something more. And to truly supercharge our speed, we introduce an in-memory cache like Redis, which you can see here, which is the second optimization which we would do on our service. So the logic is very simple over here. Whenever the client calls this get API with the short code, we immediately that request goes to the primary server and it checks into the Redis or our cache. So if it's there, we redirect immediately without even touching the DB. But if that is a cache miss, then we update the cache for the next user, and basically we redirect that request to the database and get the long URL and then redirect the user using a 302 redirect. So by using appropriate cache and invalidation techniques, we ensure that the data stays fresh in the cache as well. So while this will severely increase our performance, because with respect to memory, cache is very limited. We cannot have everything into our cache. So this cache invalidation strategies, we will have multiple algorithms implementing this, let's say LRU or let's say LFU. There are many algorithms which you can implement to invalidate the items into the cache as in the time goes. So this effectively moves our bottleneck from disk speed to wire speed now. Now, if you see our whole architectural diagram, it looks like this. Initially, we just had these three things, which is client, primary server, and DB. Now we have introduced this cache, and cache obviously has a short code and a long URL. And as I told that first we check in the cache. If the cache is not there, then we check into the DB. So this was the first thing. This is the second thing which we do for the cache. If it is in DB, we will go into the DB and check it. Okay, so the next thing what we would do is, for a global system, we have to fight the speed of the light. With actually, if a user in India clicks a link and our server is in New York, then that's a long trip. And that is why we come to the third thing, which is utilizing the CDNs and edge computing. So here we can utilize CDNs and edge computing in a way that we can serve the short URL domain by deploying our redirect logic to the edge functions basically. So for edge functions, we for like having the redirect logic, we usually have Cloudflare workers or AWS, basically Lambda Edge. These are the two services offered by Cloudflare and Amazon to basically have a redirection logic as well onto it. So here the main thing over here is having our servers as close as to the users, so that no user from India actually makes a call. If a user from India makes a call, the call shouldn't go to a server in New York, because then it will add the latency. So, but with this speed, there are some trade-offs as well, because edge functions are sometimes very expensive. And also setting this edge functions is also a challenge sometimes, because it requires extra configs and extra understanding as well, like how do these edge functions work. And also sometimes with respect to the cost, as I already told, it is expensive. We need to be very we need to be very particular in what details we are going to store on this particular CDNs, and what data is going to be contacted by these edge functions, or whatever the logic is written on the edge servers which we have. And this edge functions are having very limited memory as well and execution. Like, we cannot have a very complex logic for routing the users. We need to have a simple logic, because their execution time and memory is also very limited. So now that we have optimized for latency, now we need to talk about the massive scale. So when we talk about the scale here, we already mentioned in our non-functional requirements that we will be dealing with 100 million URLs daily, and 100 million daily active users as well. And we got to know that we need to manage 36.5 TB of data over 10 years. While this is manageable, it requires a specialized architectural approach. The first thing, when we were talking about this 36.5 TB, we cannot rely on a single database instance. And that is why we need multiple DB instances with a perfect sharding strategy. So this will help us to distribute our data across multiple instances and ensure that the load is perfectly balanced. Now the second question which comes over here when we talk about the scale is, what if the DB goes down? And that is why we implement DB replication, where we maintain multiple copies of our data on different servers along with this periodic snapshots which we can take. This will ensure high availability and data durability. So this comes under the backup, so that overall this replication and backup structure makes our system more uh, resilient And even if our db goes down, this helps us in restoring it easily, because we'll be having multiple copies of our db, and we also would have backup as well, so that even if we lose any kind of data, we should be able to get back all the data which was or which might be lost. The second thing which we talk here is about, can we scale reads and writes separately or not. So in a system, the read traffic for redirects will far outweigh the write traffic for creating the new urls. To handle this, we try to follow the microservice architecture over here, where what we would do is we would separate this particular primary service which we had earlier into a write service and a read service. The write service is basically dedicated exclusively to the creation of new short URLs and saving them to the DB. When we talk about the read service, here it would handle basically the redirects. So it first checks that if our Redis cache using the shortcode as a key to find the long URL. If it's a cache miss, it queries the DB and then updates the cache via a CDC mechanism to keep things in sync. So if we have these two services independent of each other, we can horizontally scale them also based on the load what we get and based on the what redirect traffic spikes are. So we simply spin up more instances of the read service without affecting the write service. And an API gateway is the one which will be sitting in front of this services and routing the traffic appropriately to this particular microservices based on what is the type of the request. So here I have tried to create the final high level diagram for how our system would look like. So initially we know that we'll be having a client which will be interacting with a API gateway or a load balancer, which will distribute the traffic based on what the request is. So here read service will basically get this get call and write service will get the post call. So we have already discussed how this read service will independently work, where firstly it will be connected to the caching service, where if the data is within the cache, it is good. If it is not, we'll search into the DB. So this actually reduces the load on our DB. And also we keep this cache and DB in sync using the CDC pipeline, which is change in data capture. Now, when we talk about the write service, we just have post/urls call, which is now a separate call to a separate service where we save the URL into the DB if it is there after the validations which we discussed are done. So with this our journey for a simple URL converted to a global distributed high scale system is completed. So by combining this mathematical intuition with advanced caching and microservices, we have successfully built a design that is truly production ready, I would say.